Okay, hey everyone, this is going to be a video walkthrough on question 1 on exam prep week 12 on sorting. Okay, so in this question, what we're given is a series of steps.
I
Okay,
didn't get that. Could you try again?
okay, somehow activated when I talked, which is unfortunate. Okay, anyways, so we have a series of steps that were performed by some sorting algorithm. Okay, so for each part A, B, C, and D, we need to figure out which sorting algorithm was actually used such that these were the steps. And what I want to emphasize is that these steps aren't necessarily in consecutive order, they're just some steps in the process of sorting. Okay, so let's begin with this first input list. We see here that this is the starting state. Okay, this is the starting array. Okay, so we should try to figure out how the starting array changes from this green state to this yellow state. Okay, so how it changes is we can see that all of the elements match up correctly except 192 and 1337 swap. Okay, so with this in mind, let's try to figure out which one of these algorithms that could occur in. Okay, so looking at these algorithms, we see that it could possibly be insertion sort if we're at some stage in insertion sort where we're trying to move 192 and we move it one to the left, right? It could be one stage of insertion sort. So this is valid so far. We can eliminate selection sort, right? It can't be selection sort because in selection sort, we take the minimum and in one swap, we move it all the way to the front, right? And that's not even the minimum. The minimum is 129. Okay, so we know that's definitely not selection sort. Could it be merge sort? So in merge sort, what happens is we kind of break up all of these passes into like lists of size 1, and then we kind of merge them together. So we see here that it could indeed be merge sort if we're merging 1337 with 192, and then they would be sorted relative to each other like so. So it could be merge sort. Could it be quick sort? Well, it doesn't seem to be quick sort because we haven't really chosen pivot, so I'll eliminate it for now, but I'll be cautious in the future if we ever see a pivot arise. Could it be heap sort? So again, with low probability, because in heap sort, what generally happens is we have some big element, let's say 9001, and then we move that all the way to the front. Okay, so with that in mind, the only two possibilities left are insertion sort and merge sort. Okay.
Okay, so I had to quickly put on AirPods because there was some background noise. Sorry about that. Okay, anyways, continuing off where I was going. Okay, so what we're left with, it could possibly be merge sort, probably not heap sort because 9001 would go to the front at some point in heap sort because that's how heap sort works. Okay, so with that in mind, let's look at the next step. Okay, so what happens at the next time around is that 192 moves here, and then 129 moves here. Okay, so since we see like we have these changes that's happening here and here, we can eliminate insertion sort because insertion sort would have fully moved 192 to the left before dealing with 129 here, right? Okay, so with that in mind, what we can deduce is that it has to be merge sort, right? Just because of eliminating all the other options. But we still should get some justification for why it is indeed merge sort. Okay, so what I'm going to do is look at some of these later passes, and I think it'll make sense. So if we look here, we can see I'm going to break it up into different sections. Okay, so we can see that when I break it up into these passes, let's say like these are small chunks. Okay, okay, so what we can see is that these yellow chunks get merged together, right? Like so. And then what we see is that these yellow chunks get merged into these orange chunks in the next pass. Okay, So we see that what we're doing is just merging these chunks together, and that's indicative of merge sort. Okay, so let's move on to the next one. So for the next one, let's look at this starting state right here. Okay, and what we should notice is that in the given input list, the only change so far, I'm gonna get rid of some of this starting stuff, give me a sec. The only change from the input list to right here, actually there's many changes, but one prominent change is that 1429 takes this middle position and stays here, okay? So why is that significant? Well, 1429 in this middle position is in its correct position in the final array, right? Because this is where 1429 should be, okay? So if in the first pass, we take this element and we put it in the middle, it kind of looks like a pivot that's partitioning the array, right? So let's look at some justification for why that indeed is the case, okay? So what's happening here is that we took 1429 and then we move it in the middle right here, okay? And then what happens, we can see, is that 1337, 192, 594, right, 129 and 100 all move to the left-hand side. And then what we can see, actually, yeah, all of these elements, they move on the left-hand side. That's my bad, the left-hand side. And then we can see that these yellow elements right here, they move on the right-hand side. So with that in mind, what that looks like is a partition using quicksort, okay? So this is one partition of quicksort, okay? So continuing with that logic, what we could then realize is that 1337 would be the next pivot here on the orange section. And indeed, what we do is we move 1337 in this new position, and then we copy the remaining orange like so, right? Similarly, what we can see is that making 3291 the pivot doesn't really change anything, okay? Nice. And let's just keep the cool color scheme going, right? And then what we can do is perform one more pass. After choosing 192 to be the pivot, we see that indeed it partitions around 192. And just for sake of, I don't know, conciseness, I won't look at this next example, but we can safely conclude that it is quicksort. So quicksort. And then I can highlight my answers just to be a bit more verbose and transparent in red. So first one is merge sort, second one is quicksort. And on the topic of quicksort, we can see here that all we're doing is the simple 3 scan. It's not necessarily Hoare partitioning. Okay, just a quick aside. So looking at the next example, let's get rid of some of this clutter again. Looking at the next example, we see here that this section of the array never changes, right? So an algorithm that wouldn't change this part of the array is something that does work on the left-hand side first, right? So what algorithm kind of grows the list from this side, okay? The algorithm that grows the list on the left-hand side is insertion sort, right? Selection sort also grows the list from the left-hand side, but it pulls elements from the right-hand side, right? How insertion sort works is that it only does stuff to these elements on the left-hand side, and it doesn't touch the elements here until later passes, right? So immediately off the bat, we know that insertion sort kind of grows from the left-hand side like so, so it should be insertion sort. But let's justify that for ourselves. Okay, what we can see here is that the first thing that changes is that 1337 moves to the front. Okay, for 1337 to move to the front, we see that it compared itself to 7683, 3291, and 1429, and it was less than all of them, so it swapped all the way here, right? And then we can also conclude more notice that none of these other elements have changed. So with that in mind, all we did up to this point is that we looked at 1429, 3291, 7683, and 1337 in insertion sort. Except let's continue that process just to make it official. Okay, so after this point in the algorithm, what we're going to do is we're going to look at the next element to move. So we look at 192 and we see that 192 moves to the left. So what that's telling us is that we swapped 192 with every element before it, and now we see in insertion sort, this is our partially sorted array that grows over time, right? And this was it in the first stage. And then we could see here that the next thing that we do is take 594 and move it over here. And what that does is it grows our partially sorted array of this size. Okay, so what we're doing is just calling insertion sort. And in these examples, what we did was move 192 to the front, was move 1337 to the front, and was also moving 594 to the second position. Okay, perfect. Nice. Okay, so looking at this last example, the first thing that should strike you guys as weird with this sorting example is that somehow we took 7683 and promoted it to the front. Okay, so why is that weird? That's weird because in very few sorting algorithms, it makes sense to do negative progress. What I mean by that is usually bigger elements tend to move to the right. Smaller elements tend to move to the left. But in this sorting algorithm, somehow a bigger element moved to the left. So let's walk through our algorithms here and ask ourselves, in which algorithm is it possible for a bigger element to move to the left, right? Insertion sort, that would never happen because insertion sort, every time we swap, we're basically moving an element to the left, right? If it's smaller than what's already there, okay? And we can see here that 7683 is definitely not smaller than the other elements that were there in the beginning. Selection sort also wouldn't make sense because we just move the minimum to the front each time. Merge sort wouldn't make sense because in merge sort, what we're doing, if you guys recall in part A, is that we take these subsets of arrays and we constantly merge them together. That doesn't mean that 7683 is going to go to the right, right? That's no way that could possibly happen. It could partially move to the right, but it wouldn't move all the way to the start, okay? Okay, so the next thing that we notice is that in quicksort, in order for 7683 to move all the way to the left, right, that means it was somehow less than the pivot, but that doesn't make much sense because if the pivot was 9001, which is the only way for it to move left, then it wouldn't somehow jump past all of these other elements. So we can safely eliminate quicksort. And then the last thing that we're left with is heapsort. And immediately looking at heapsort, this should make sense. Why we have the biggest element, or not the biggest element, the second biggest element. Let me correct myself. It makes sense why the second biggest element's on the left, because in heapsort, what we do is we create a max heap. So in the process of creating a max heap, what we should notice is that we put the biggest element at position 0, such that when it's removed, it moves to the end. So we see here that this red state of the array occurred when 9001 was initially the first element. It was removed and moved to the end. And then we could see another iteration of heapsort occurs when we remove 7683, we put it at the next position, right? So with that in mind, we see that it is indeed heapsort because the biggest element, or the second biggest element, 7683, is in the beginning, and we're growing our sorted array from the right-hand side. Okay, so that's all for this video walkthrough. I hope you guys found it helpful. and I didn't fill in the answer, so I'll do that shortly. Yeah, but keep on the lookout for more videos because they're on their way. Okay, see you guys.